Okay, the question, excuse me, came up about these tree diagrams that you see in your text, the OpenStax Calculus 3 text, which is multivariable calculus. Okay, so yeah, here's the tree diagram, and let's just explain this. You have a function f of x, y. So you know you can take a partial derivative of f with respect to x or a partial derivative of f with respect to y. Now, the partial derivative of f with respect to x tells you the rate at which the value of the function changes as x changes, the rate at which f of x changes with respect to x. So that if x changes by a certain amount, you multiply that by the rate at which it changes with respect to x, and you get the change that results in the function. In this case, it would be an approximate change because the rate of change naturally changes as x changes. But if you have a very small change in x, multiplying this rate of change by the change in x gives you a very good approximation of how much x changes. Okay, in any case, this is the rate at which this function changes due to changes in x. In other words, the rate at which it changes with respect to x. And fy, of course, gives you the same thing for changes in y, okay? If you multiply a small change in y by the value of fy at some point, you're going to get the approximate change in the function due to that change in y. And then if you add the change due to a change in x to the change due to some other change in y, you get the net change in the value of the function. That's the basic idea of partial derivatives. And that's confirmed by everything we've done recently involving tangent planes and the relationship between tangent plane and differential. And what I just explained is essentially the differential. df is fx delta x plus fy delta y. Okay, that's rate of change in the x direction multiplied by the change in x, rate of change in the y direction multiplied by the change in y. I've left a few words out of there. It's rate of change of x with respect to x times delta x, etc. But we've talked about all that. Now, of course, x might be a function of s and t, let's say, and so might y. Okay, so if x is a function of s and t, then we can say something very similar about the x function. That is, if you take the partial derivative of x with respect to s and multiply it by the change in s, you get an approximate change in x. And if you take the partial derivative of x with respect to t and multiply it by a change in t, you get the change in x due to the change in t. So the rate at which you change due to a change in, well, okay, f sub x is the rate at which f changes with respect to x. X sub s is the rate at which x changes with respect to s. So if you have a change in s, that gives you a change in x, and that change in x then results in a change in f due to the fx. And the rate that you get from the fx and the xs is fx times xs, okay? If a change in s causes x to change by 2 units, now that's kind of a big change, but we'll take that, then f will change by fx times that 2 units. So that the rate of change, now I just wrote rate fx ss, yeah, I think I said that, xs, I think I said it right. This is the rate at which f changes due to the change in s and its effect on the x coordinate. Now, you can also have a change fy, ys. A change in s causes y to change, And the change in y then, coupled with Fy, gives you the change in F due to the effect of S on the change in S on the y coordinate. Okay? So I could write down some words around this. I didn't want to write down too many words in class. That might help. So this is the rate of change of F due to the effect of a change in S on the value of X. Okay, so S changes by a little bit, causing X to change at this rate. So you get a change in X, which you multiply by Fx to get the change in F due to that effect of that change in S on X. Now you have a similar thing down here. So that's this. This would be rate of change. And I said rate of change of, it should be rate of change of F, and that's getting a little hard to read, I know. Rate of change of F due to the effect of delta S on your y coordinate. Now I'm not going to write it out, it's already getting cluttered enough, but this would be what? Well, think about what that would be. What rate would this be? It would be the rate of change of F due to the effect of a delta T on X. So I could write just the last part of that phrase, if you can agree to understand that the first part of the phrase mimics these. Dot, 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 okay. This would be due to the effect of delta T on X. I can't even read that X. Okay, so delta T changes. X changes at a certain rate with respect to T. So you multiply that rate by your delta T to get a change in X. And then you multiply your change in X by Fx to get the change in F due to the effect of that delta T on X. And then this is the same thing. Due to the effect of delta T on Y. So you have function f of x, y, and x depends on two parameters, s and t. So does y. Change s by a little bit, well, it changes x. And then due to the fact that you have some rate of change of f with respect to x, it changes f. And then a change in s also causes y to change. And you multiply that change by fy to get how much f changes due to the effect of the change in s on y. So change in s makes x change, which then multiplied by fx tells you how much that affects the value of f. And then same thing with y. It's a lot to sort out. It's not easy, but hopefully this will be helpful in understanding how these quantities go together to give you a partial derivative of f with respect to s or with respect to t or a differential. Okay, so understanding this, understanding the two descriptions in purple, we see we have the rate of change of f due to the effect of delta s on x, that's fx delta x, and the rate of change of f due to the effect of delta s on y, that's fy ys. Then the total rate of change of f with respect to s would then be the sum of these two changes, fxss, fxxs, fy ys. And we add those, there's a plus in there. Okay, and similarly with respect to t. Then we can write down the differential, which just says basically the change in f due to a change in s and a change in t is going to be the sum of, well, the effect of the change in t, which would be fx xt delta t plus fyyt delta t, just this expression, plus this expression, which is the change, the rate of change with respect to s. Now, in both cases, we've multiplied the rate of change. If we multiply this rate of change by delta s, that gives us the change in the function. And I didn't really write that step down, so I don't really have room to write it. I don't want to clutter the board. If I take the total rate of change of f with respect to t, which is this, and multiply it by delta t, then that's going to give me the approximate change in the value of f. So here you see that this constitutes this expression multiplied by the change in t. And if I multiply this expression by the change in s, that will give me the total change, approximate change in the function due to the change delta s. Okay? Now, let's discuss this a little bit more. Clarify the notation even a little bit more, clarify the idea just a little bit more, but that's pretty much it.